Okay, so now we're going to go ahead and jump into the rest of the Chapter 9 slides. We've covered pretty much the hardest stuff, so now it's kind of downhill from here, thank God. So let me go ahead and start sharing my screen, and we can finish up these slides here. Okay, so we're jumping into type 1 and type 2 errors. So this is talking about when, oh wow, I made myself that big. Okay. So this is talking about, oops, this one, let me go back. Okay, there we go. So in research, we want to balance the probability of obtaining a type 1 and type 2 errors. And type 1 and type 2 errors are different conclusions or problematic conclusions that we can make when we are running t-tests and ANOVAs and all different kind of statistical analyses. So a type 1 or type 2 error is where we make the wrong kind of conclusion about our data. So the type 1 error is where we make the wrong conclusion, where we are rejecting a null hypothesis that is true. So basically what that means is that we are saying that there's a significant result when there isn't one. So let me write that. So claiming to have a significant when in reality there isn't one. So type 1 error is where we claim to have significant results. We're rejecting the null hypothesis. However, the null hypothesis is true. So there isn't a significant result happening. So that's type 1 error. So that's the one type of wrong conclusion you can make. Type 2 error is basically the opposite. So it's where we retain the null hypothesis, or we're saying that there's no significant result, when in fact there is. So let me write that out. So claiming there is no significant result when in reality there is. So type 2 error is where we're saying no significant results are happening, however in reality there is significance happening. So that's type 2 error. Type 1 error is also called alpha, and type 1 is called beta. So our goal as researchers is to balance the probability of these two things occurring. In this case, we're being too liberal. We're saying that there's a significant result when there isn't one. Type 2 error, we're being too conservative. We're being too stringent. We're saying that there's no significant result when there is one. So we want to be moderate. We don't want to be too liberal. We don't want to be too conservative. We want to be in the middle so that we can find a significant result when there actually is one, and retain the null when the null is true. So that's the goal here. So here is a good way to remember the difference between type 1 and type 2 errors. If you've heard the story of the boy who cried wolf, he caused type 1 and type 2 errors in that order. First, everyone believed there was a wolf when there wasn't. Next, they believed there was no wolf when there was. So you substitute effect for wolf and you're done. So basically, at first, the townspeople in the story believed there was an effect. They believed that there was a wolf when there wasn't. So that's type 1 error, saying there's an effect when there isn't. Next, the townspeople were told that there was no wolf when in fact there was. So that's type 2 error, when we're saying that there is no effect when in fact there is. So you can remember type 1 and type 2 errors using that story. You can also use this little Punnett square deal here as well. So effect found in nature, no. Experimentally found, yes, so that's a type 1 error. So if there is no effect in nature, however, we found one experimentally, that's a type 2 error. You can also call this a false positive and a false negative, which I have a picture of that here. So type 1 error is a false positive, so that's a man being pregnant. Type 2 error is a false negative, so this woman is clearly pregnant, but the doctor is saying that she's not. So that's another way to remember it. And there's Mark joining us again. The type 2 error, the best you never had. So here are some notes about P. We talked a little bit about P. So here are some notes about it. Remember that our goal is to get P of less than 0.05. So in this case, we are rejecting null. And we have a P of greater than 0.05. Not rejecting, rejecting. We are retaining, null. Retaining the null. Okay. So that's this thing. So here are some notes about P. P is not the probability that HO is true. It's not the probability of type 1 error. It's not the probability that the data are due to chance. It's not the probability of making the wrong decision. However, why is this not letting me? Okay. So P is, for any statistical test, P is the probability of the data observed if the null hypothesis is true. So the data observed is the stuff that we gather, the data we gather. It's the probability of the null hypothesis being true given the data that we have. So that is P. P is the probability of the statistical test value. And this is a very famous meme that stats nerds love to use with Ryan Gosling. Your P must be greater than 0.05 because I failed to reject you. Okay, so why do we use an alpha level of 0.05? The adoption of the alpha level of 0.05 is to protect against type 1 error and also balance type 2 error. So it's kind of the mid-ground. So this is talking about type 1 and one-tail and two-tail tests, but we've already talked about this, so I'm not going to go too much into it. Remember that these are the symbols for the two-tailed test, and these are the symbols for the one-tailed test. I've already gone over that in the previous video, so you can look at that there. So that's one-tailed and two-tailed with the symbols, and I wrote the graphs for these as well in the previous video. So this is, again, kind of defining what one-tailed and two-tailed are. I've talked about it already a little bit. So a two-tailed significance test is one where a difference in population means can detect positive and negative differences. So that's this one here at the bottom. So remember, like I said in the previous video, we use two-tailed tests when we're not really sure how our data are going to fall. So if we are not sure whether we're going to get a positive or negative result, it would be more prudent to use the two-tailed t-test because it is sensitive to both positive and negative extreme results. One-tailed t-test, on the other hand, is a statistical test for a difference in population means or negative difference, but not both. Oh, that should say positive, not population. So a difference in positive or negative differences. So here's your positive example, here's your negative example, but we don't look at both, we only look at one. So we would use a one-tailed t-test when we are more sure about how our data are going to fall. There's been previous research in this area that has helped us determine whether we're going to get a positive or negative result. So this is how your alpha level of 0.05 works for one-tail and two-tail. So for a one-tail, this can be either on the left or right. Our 5% alpha level of 0.05, so our 5% rejection region is only on one side. So we have a shaded region that can even be on either side of the distribution, and it's 5%. When we have a two-tailed test, however, we've got to cut that 5% in half. And when you cut 5% in half, you get 2.5% on each side. For those critical thinkers out there, you can see that the rejection region for a one-tailed t-test with an alpha level of 0.05 is bigger than for a two-tailed t-test with an alpha level of 0.05. Because we've cut that 5% in half, our rejection region is smaller. So basically what that means is, because our rejection region is smaller, So this test is a little more conservative. Because we have a smaller rejection region, we've got to get a really big T value in order to reject the null hypothesis because we have a smaller rejection region. A one-tailed t-test, on the other hand, is a little more, rejection region is larger, so it's a little more liberal. We can get something, you know, a little more close to the center of the distribution and still reject the null hypothesis, so it's a little bit more liberal. So that's how one-tailed and two-tailed works. You have to have a bigger t value in order to reject the null hypothesis when you have a two-tailed t-test as opposed to a one-tailed t-test. So that's something to keep in mind. With two-tailed, we're a little more strict. One-tailed, our rejection region is bigger, so we're a little more lax. So that's that. Okay, so now we have gone over how to calculate your t value. We've talked about type 1 and type 2 errors. We've talked about one-tailed and two-tailed, all that good stuff. So what should I do now? Well, we've got 2 more steps to do, so let's talk about those. The first of these 2 steps is the confidence interval. So our t value tells us whether or not we have a significant result. So that's where we've gotten so far. The confidence interval, on the other hand, is another statistic that uses sample statistics to establish 2 limits, an upper limit and a lower limit. The population parameter is expected within a particular degree of confidence to be within this interval, within these 2 limits. So basically, the confidence interval is the range in which we expect our data to fall for the population. They're most often used with other population parameters as well, and we're most likely to use a 95 or 99% confidence interval. So let me write a few more notes about these. So when we have a 95% confidence interval, we have an alpha level of 0.05. So when we're talking about having a 95% confidence interval, that means we have chosen an alpha level of 0.05. So say in your project that you have chosen an alpha level of 0.05, that means at the step where I'm asking you to calculate your confidence interval, you're going to say that you're calculating a 95% confidence interval because these 2 things are associated with one another. When you have an alpha level of 0.05, you're calculating a 95% confidence interval. However, if you've got a 99% confidence interval, you've got an alpha level of 0.01. So these 2 things go together. Our alpha level, I did not spell alpha right, of 0.01 is associated with a 99% confidence interval, and alpha level of 0.05 is associated with a 95% confidence interval. So again, the confidence interval is the range in which we expect our data to fall. So here's your formula for confidence interval. It's really easy because we pretty much have all this data by the time we get to this step. We have all this information, it's just putting it in the formula. So we have our sample mean by this point. The TA here, that is, and I want to make sure that you all understand this because the book does not do a very good job of this. So TA is our critical value. So I would write that down in your notes. So this TA here, that's our critical value. That's the thing we get from the t-table. So for that Doritos example that we did in the previous video, our critical value was 2.365, I believe. So that would be our TA in this example. And our S subscript X bar is our standard error of the mean, which we calculated in previous steps as well. So you have all this information. So you put this into the formula for the lower limit. You're subtracting these things from one another. With the upper limit, you're adding these things to each other. And you write it like this. So say that we had a lower limit of 3.5 and an upper limit of 7.9. So you would write your confidence interval like this. 95% confidence interval, 3.5, 7.9. So this is how it's written. So we're doing a 95% confidence interval, and your lower limit is 3.5, upper limit is 7.9. So that's how you do that. Another note about confidence intervals that's important. So, and this might be kind of difficult to explain when I don't have a board to write on, but so say we are, we've calculated our confidence interval. Let's do that again. Undo. Say we've got a number line here. And we have, we've got different points on this number line. Say we've got negative 2.5, let's just go like this, negative 2. Negative 1.5, negative 1, 0. Five, 2. Okay. Here's our number line. These are not very evenly spaced out, but we get the idea. So here's your number line. You've got your negative side and you've got your positive side, and you have 0 in the middle. If you get a confidence interval that passes through 0, so say I had a confidence interval that was 95% confidence interval, that was negative 2.5, 1.5. So my upper limit is 1.5, and my lower limit is negative 2.5. This one passes through 0, right? Because the lower limit is over here somewhere, and my upper limit is right here. It passes through 0. And when that happens, we need to retain the null. Because it's passing through 0. And if you remember from our discussions with z distributions, the mean for a z distribution is 0, remember? It's in the middle of the distribution. So if our data is passing through the middle of the distribution, 0, we need to retain the null, because remember, we only reject the null hypothesis, we only get significant results when our results are out on the fringe, when they're out on the edges of the distribution. So when our confidence intervals pass through 0, we need to retain the null hypothesis. However, if they don't, let's do another. So say we have a 95% confidence interval of, like the one I put down here, 3.5, 7.9. That doesn't pass through 0, right? Those are two positive numbers. So in that case, we're going to reject the null. Because those two numbers don't pass through 0. They're both positive numbers. So we're going to reject the null in that case. So whenever you have a confidence interval that passes through on the number line 0, we're going to retain the null hypothesis. However, if you've got both negative numbers or both positive numbers, you're going to reject the null. So that's a good way to check your work. When you've gotten down to this step and you found that you have a confidence interval that passes through 0, however, in previous steps you rejected the null hypothesis, there's a discrepancy there that you need to figure out. Maybe you made a math error somewhere or something. So I would keep that in mind. All right. So the 95% confidence interval is the basis for the margin of error. So this is the margin that we expect our data to fall within. The last point here is about our effect size. So after we have conducted our t-value, after we have we've determined whether we have significant results, after we've conducted our confidence interval, last thing that we're going to do is our effect size. And effect size is very, very important. So we do it every time, even if we don't have a significant result, because our effect size tells us the magnitude of the difference between our two groups. It tells us how big the difference is between our sample and our population. So effect size is very important. So here's your formula for effect size. The measure that we use is called Cohen's d, which I believe might be on the next slide. Let's see. No, it's not. Let me write it down. So Cohen's d is the measure effect size that we use, called Cohen's d. So that's how I will refer to it. All right. So here is our Cohen's d formula. So here are different pieces. We have our sample mean, which we've already found by this point. We have our population mean, which is given to you. And you have your S hat, which is your sample standard deviation. So at this point, you have all of these figures. You just need to put them in the formula to find your Cohen's d. So pretty simple formula there. So again, our effect size, or our Cohen's d measure, is the amount or degree of separation between the two distributions. It is how big of a difference we have between our two groups. So we have a Cohen's d of 0.20. That's what the overlap looks like. Cohen's d of 0.5. We have more separation. Cohen's d of 0.8, even more separation. So here's a good interpretation of Cohen's d. When you have an effect size of, I'm going to write a little bit more specificity here. So when you've got a Cohen's d value of 0.1 to 0.3, that's in the small range, small difference. If you've got a Cohen's d value of like 0.4 to we'll say 6.5. You know, these are kind of arbitrary, and I'll talk about that in a minute. That's kind of a medium difference or moderate difference. Next we have 0.7. So again, with Cohen's d, these are not rigid guidelines. These are kind of flexible. So somewhere in the 1 to 0.35 range, that's kind of small. In the 0.4 to 0.65 range, that's medium to moderate. Anything above 0.7 or 0.8, that's large. It's also important to keep in mind that these are absolute values. So even if you get a negative 0.8, that's large. Even if you get a negative 0.2, that's still small. So these are absolute values. So that's how you interpret your Cohen's d. So P, which is the probability of our null hypothesis being true given our observed data, and D, which is our effect size, tell you different things about the population the sample is from. So P tells you whether the population you sampled is different than the null hypothesis population. So in other words, this tells you whether or not there is significant differences. So P tells us whether or not we have a significant difference happening. D, on the other hand, tells us how big the difference is. It's talking about magnitude. So D tells you the degree of separation between the sample mean and the population. So how big the difference is between the sample and population. What is the degree of separation there? So these tell us different things. So our t-test tells us whether or not we have a significant result. So it's a kind of binary thing. It's either yes or no, whether we have a significant result or not. D, however, tells us how big that difference is. And it's funny though, because even if we have a non-significant result, we might get a big difference. And the reason for that might be due to a lot of factors. One of the biggest ones is sample size. So we'll see that if we have a small sample size, we might get a non-significant result. However, when we run our Cohen's d analysis, we'll see that we have a large difference. So that might tell us that with more people, with a larger sample, we might obtain significance. So these two things kind of work together. They tell us about what's going on. Okay, so I think that's our last slide. Yeah, I really like this meme. So if you don't know what a p-value is, you can still ask. If you have any questions, feel free to email me, because it's really important that we understand this chapter, especially because a lot of these concepts will carry on throughout the quarter. So if anything is confusing, please feel free to email me. I'm also going to post a video of me working a single sample t-test problem from beginning to end. So that's another good resource. Let's see here. No, go away. So I typed up kind of some steps for the null hypothesis significance testing method, and I want to go ahead and share my screen so we can talk through them, and that'll be the last thing that we do. Okay, so here are your null hypothesis significance testing method steps. The first one you're going to do is you're going to state your null and your alternative hypotheses. So remember that the null argues that there is no significant results, and the alternative argues that there is significance. So that's the first thing we're going to do. We're going to state our null and our alternative hypotheses in terms of the experiment. It means that we're going to discuss the variables. We're going to discuss the variables being used. So like for the Dorito example, we talk about the sample weight. Ooh. We talk about the sample weight and the population weight of the Dorito bags. Next, we're going to choose whether we want to do a one-tailed or two-tailed test. So remember that when we have a two-tailed test, we're not really sure how the data are going to fall. It's a little more conservative because our rejection region is smaller. And we can also do a one-tailed t-test if we are kind of certain about how the data are going to fall. And it's a little more liberal because the rejection region is bigger. Next thing we're going to do is we're going to pick a alpha level, usually 0.05. However, if you want to be more stringent, you can pick 0.01. 0.01 alpha levels, they're pretty common in like medical research because we want to be really certain about a result before we go giving people drugs and that sort of thing. So if you want to be really conservative and really stringent, you could use a smaller alpha level, but most of the time we use 0.05. Oh, I forgot a step here. We also need to find our degrees of freedom. Ooh. Remember that this is n-1. So we find our degrees of freedom. We take our sample size, subtract from 1. We have our degrees of freedom. So we use this information. We use info from steps 2, 3, and 4 to find our critical value in our t-table. So this is the point at which our rejection begins. Our critical value begins our rejection region. So we've got to find that. If you're doing a two-tailed t-test, critical value so if you're doing a two-tailed t-test, your critical value is going to be both positive and negative. So like we saw with the Doritos example, we had a negative 2.365 and a positive. Then you're going to gather your data. Then you're going to run your t-test using your t-test formula. Then you're going to compare your calculated t-value that you get from step 7 here with your critical value that you get from step 5. If the t-value exceeds the critical value, we're going to reject the null hypothesis because it's falling within the rejection region. If our t-value does not exceed the critical value, or it doesn't fall within the rejection region, we're going to retain the null hypothesis. And there's no significant results happening there. So we do that. We find whether or not we have a significant result. After that, we're going to calculate our confidence intervals. So remember, this is our lower limit and upper limit. And remember that 95% confidence intervals are associated with an alpha level 0.05 and 99% confidence intervals are associated with 0.01. So 99% confidence intervals are associated with an alpha level of 0.01, 95% confidence intervals, alpha level of 0.05. Lastly, we're going to do our Cohen's d. That tells us the magnitude tells us how big the difference is between the groups, or the magnitude. So I will go ahead and post this little cheat sheet here on Moodle so you guys have this as a resource. This right here, these 10 steps, can be applied to just about any statistical test we're going to be running for the quarter. So not only single sample t-tests, but also the different types of t-tests that we will be talking about in Chapter 10, as well as ANOVA and correlation to some extent as well. So all the different analyses that we're going to be talking about until the end of the quarter use this, this concept here, these steps as well. So it's really important that we understand everything that's happening here. So if you have questions about this, please feel free to email me about that. And that is all. Again, email me if you have any questions. Have a good day.